the problem as well. Okay, so let us start with this steel bracket that is experiencing a distributive load of 50 pounds per square inch on the top surface of here, and then this bracket is fixed at these two locations here, and we have to figure out the deformed shape, how much deformation this thing is experiencing, as well as our von Mises stresses distribution. So you guys should already be aware about von Mises stresses that we are looking for here. Okay, so first of all, we have to create the geometry of this thing. So we have this thing. Let me move to our workbench here. So let's first start by defining the material. So we have steel, and for the steel I'm using isotropic elastic property, and the value of Young's modulus is given to us, and that is 29 exponential, or sorry, 10 raised to power 6, and a Poisson's ratio of 0.3. So this information is provided to us in the question here. Okay, so once we have defined our material, let's close this engineering data and next move to the geometry. Okay, one more thing. So we started with static structural. So all you have to do is double click this static structural, and this box will start appearing here. Okay, next click on the geometry. It will take some time to open our space claim, and once that thing is open, you will see an environment like this here. Okay, so first of all, before we start drawing, let us consider the units here. So going to the file in space claim options, let me define the units first. Okay, so I have units here, convert from metric to imperial, and the length is in inches. So let's do inches here, click OK. Okay, now since we have a bracket that the top surface is 3 by 2 inch, so we can start by creating a square here. So let's or a rectangle. So it's 3 inches by 2 inches, and the total height is also 3 inches with a thickness of 1/8. So let's pull this thing up. I have 3.125. Okay, so that's the initial structure. Now since 3 of the sides are removed from our geometry here, so let's do a shell command, and let's select this thing in here. Okay, and it's already given by default of 1.25 inches. That is the thickness of the place that we are getting here, so you can modify that thing as well. But since in our problem we already have 1/8, so that is fine for our case. Now next we have to, let's consider this face. Okay, now this particular face is cut in half, so let me draw a diagonal. Okay, now let's do the 3D mode. See this thing here. Next, I'm selecting the pull command. Again, selecting this particular face that we have created. Let's just pull it in the opposite direction to remove this structure here. Okay, now it looks much like our steel bracket that we were looking for, but still we have to create two holes on this particular surface. So let select here, and from the geometry I know that it is 1 inch in the horizontal direction and 1 inch in the vertical direction, so our circle lies somewhere here, so I can use the construction lines. Okay, and let's define, I have 1.125 here, and then I have 1 inch going up. Okay, so here will be our circle having the diameter of 0.5. Okay, and the next one is 1 inch from this center. Okay, now next I'm clicking 3D mode. Once this thing is constructed and I have this structure here, now I have to remove these circles and create holes here. So again I can use the pull command and select the circle and just move it backwards, and the hole is being created here. Same thing I can do here, move it backwards. That is done. So this is our final structure here. Once this is done, we can save this thing and close our space claim here. Okay, so here you can see that geometry also we are seeing a green color tick, so we are good here. Next, let's move to our model. Double click that, and it will take a little bit time to load this thing. Okay, so now our model is being loaded. We can see the geometry that is here, and let's first check the units here. So the units, okay, let me close this thing. The units are correct. We are in imperial units. That's fine. Now next, let's check the material, that which material we have assigned to this. So it should be steel that we initially defined the properties for. Now, next thing is our mesh. So here there are a bunch of different things that you can do to change your mesh, and depending on your mesh, the values of stresses and deformation will also vary. So you can either add the element size. Here I'm taking as default. The next is sizing. You can define the sizing and the resolution here. Uh, Currently it is 2. So let's don't do anything. Let's just update the mesh, and it will update based on the uh, standards it has. So let's do that. Okay, so here once we update the mesh, here you can see the mesh, it is pretty coarse. It's not a good mesh here, but let us solve using this particular mesh, and then we can make adjustment to this mesh to make sure that we are getting an accurate results here. Okay, so once this is done, next move to our static structural and apply the force. We know that on top of this plate we have a uniformly distributive load. So go to environment, apply pressure, and pressure is applied on this particular face. Hit geometry, apply, and the value, the magnitude was 50 psi. So 50 psi is applied on this face. Next, we also know that our holes here, it was fixed. So let's select that, our fixed support, and let's select both of them and hit apply. Okay, so now I have applied fixed support here on the holes, and the distributive load is being applied at top here. Okay, that's all the forces that we were looking for. Now let us do a deformation, because the question asks us for the deformation as well as the von Mises stresses. Let us first start with the deformation. So let's do total deformation and solve this thing. Okay, it will take some time, so I will pause here, and we'll start once this is done. Okay, so now the solution is done, and we are getting this particular result for the deformation. So we are getting the minimum deformation of 0 inches and the maximum deformation of 0.04 inches that is present here at the very end of the plate here. But now the key thing is, how do we know if these results are correct and our mesh was okay? So we have to do a convergence test. So before to do the convergence, what we can do is, let's click at the solution here. Okay, and then here in the solution you can see that you have adaptive mesh refinement. So, and it's asking us for the maximum refinement loop, how many times you want that refinement to happen, and also the depth here. So you can change these numbers, and it will do multiple refinement and different depths as well. So let me convert this thing into 3. Okay, and then go to the total deformation here, right click it and insert a convergence plot. So here you can see that if you right click on this total deformation, you can insert this convergence. So let's click here. Now I have this convergence, and you can see that for the convergence, the allowable change here, it's written 20%. So ideally we don't want the convergence to be 0. Okay, but if you are going to do that, it will take a lot of time. The size of the cells will be extremely small, and the elements will be uh, too large to run that problem. So let us do a step by step. Let us consider the convergence of 10% initially and just hit solve. Okay, and let's see here. So initially, before we did the this mesh convergence, our initial result was it was taking around 1800 nodes, and the elements was around 800, and the total deformation we were getting was this number here. Now, since we have done the refinement, it is creating a new mathematical model and refining this. So let's see what we will get for the next iteration. Okay, so we have the result of first iteration here, and here you can see that now the value we have is it has increased the number of elements, and the percent change is 10.4. Since we have assigned the maximum allowable change to 10%, it is still higher than that. So it is doing another iteration and running and refining the mesh one more time. And you can also see the change in the deformation here. Total deformation value has also been updated here. Okay, so once the percent change comes less than 10, this thing will stop, and I will get the convergence plot. Okay, so this is the convergence plot we are getting, and it has done a couple of iterations. And now the value of total deformation is 4.57 exponent 10 raised to the power -2, and here you can see that it is starting to converge. So you can go back and look at the geometry. Your mesh is also updated here, so we have more elements here, but these results are still not correct because the convergence maximum percentage we have used is 10%. So let's reduce it to 1% and run this thing one more time and hit solve. Okay. Now this process will take time because the number of elements in your problem has significantly increased. Okay, so typically it will take, if you are using uh, so if you are using your software, the free versions, student version that you have, it is a possibility that it won't do the solution because it has a limit on number of elements or a number of nodes that you can use. So in order to do so, if you are getting that problem, you have to go to one.uttyler.edu and run your simulation through the university network. So I'm also running through one.uttyler.edu. Okay. Okay, so we have one more result for the iteration, and let's see what is the percent change. Okay, so we are still above the percent change is greater than 1, so we are at 1.2449, and you can also see the number of elements has increased significantly here. So from 16,000 all the way to 67,000 here. Okay, so it is doing another iteration to have that percent change less than 1. So for your uh, verification, either the mesh is good enough or not, this percent change should be less than 1. Okay, ideally we want it to be 0 or 0.0001, something like that, but based on the uh, time constraint, less than 1 is fine. Okay, I'll pause here and resume once this thing is done. Okay, we are almost done, so it is writing the results. Okay, so now here you can see that our results are converging, and the last change here is less than 1%, so we have around 0.3% change, and the number of elements has also increased to 223,000, more than uh, that. So if you have very nice computers, you can run another one and make it less than that, closer to 0. But for our application here, that is good enough. So let us see now the total deformation. And here you can see our mesh here as well. That is pretty refined. And also the value for maximum deformation has also changed. So initially it was 0.040 and now it is 0.046. So there is this difference here. Okay, now based on that you can also do some animations. That is the deformation, how it is happening here. Okay, next in the question it also asks us to calculate the stresses, the von Mises stresses. So here we have equivalent von Mises stresses. We can add that, hit solve, and here I have the von Mises stresses here as well, and I can add the location for maximum stress where that thing is happening. So It is happening just next to the fixed support we have. So you can add the minimum as well and have these results. Okay, so for the deformation as well, you can add maximum and minimum. So let me take this thing. Okay, so the maximum I'm getting here, and the minimum is, since it was a fixed support, the minimum is located here. Okay, so these are the results we are getting. Now another question was how to verify these results. We already discussed that you have to look for the reaction forces, and if the reaction forces balance out the applied force, then the results are good. Okay, that's one way. Next, I got a question that how we can verify by hand calculations, and that was specifically since we haven't done the 3D FE formulation. So how can we verify that? So the thing is, you are verifying this FE results with the analytical solution, so with the exact solution using your mechanics of material equations. So if a force is being applied on any structure, how can you calculate the deformation here? So based on the moment, the torsion, the stresses, you can calculate that. So you are verifying the analytical solution with the FE solution. That's how you are going to do the hand calculation. Okay, so this example shows how to do a convergence plot. Next, I will do one of the steady state thermal problem in the next clip.